Thanks for the invitation. Thanks for the introduction. So, thanks for being the first speaker, because I'm notoriously bad at picking up name tags and notoriously bad at keeping name tags. But when you're the first speaker, fortunately, you don't have to have a name tag. Okay, so actually, can we switch off the screen? Anyway, so the title is Exceptional Manifolds, and it's a work in progress, mostly done, mostly finished, and so it's a joint with Bram Petri from Bonn, then Aru Ray from Max Planck in Bonn, and also Junghwan Park, who is also right now at the Max Planck in Bonn. Okay, and so the starting point for this little project was a talk by Bram. He gave a couple of months ago in Regensburg. So let me just say one word for motivation. So he was talking about subgroup growth. So given group G and N in N, so in subgroup growth you consider the following function. So define S and G. So what is that? So that's the number of all index N subgroups of G. Okay, so it's like a standard definition. Subgroup growth, and so Bram gave a talk about, I guess, about surface groups, like what is S and G for a surface group. And so after listening to this talk, we're talking a little bit, and so here, so you look at all index N subgroups, also not necessarily normal, and also you don't care about the isomorphism types, you only care about subgroups. And so we're wondering a little bit about what happens if you look at the number of isomorphism types of index N subgroups. Why not? And so this led us to the following definition. And so since I'm more like a manifold person than a group theorist, we ended up with a definition regarding manifolds. So a manifold is exceptional. A manifold, let's call it M, is exceptional if for all N in N, all N-fold connected covers are homeomorphic. Okay, so it takes a while to digest the definition. So it's a slightly funny definition. So we say a manifold is exceptional if for any n, all n-fold covers are homeomorphic. Yes?
Yes, you might have said that this, and I might have missed it. Your groups are finitely generated?
I mean, its motivation doesn't matter. I mean, anyway, you can define. It doesn't matter. It doesn't matter. I mean, I wrote down a definition. I mean, you can define it for anything, as long as you don't write down a theorem. It doesn't matter how you define it. Also, like, okay, so I mean, okay, perhaps it was now a little bit too harsh, but anyway, like, so I'm somebody who comes from the world of nice, cute, compact three manifolds. So for me, all groups are just by definition finitely presented, almost. But yeah. Okay, so also, so perhaps, so just to avoid any confusion. So for example, like when I say manifold, perhaps one should say a little bit what do we mean by manifold. So for me, manifolds will always be compact and connected perhaps not necessarily orientable. Okay, so a manifold is exceptional if for all n-fold connected covers are homeomorphic. So let's just see whether we can classify such manifolds. So let's start in dimension 1. Okay, so let's see. So how many compact connected one-dimensional manifolds do we know? Well, we know the interval and S1. So the interval doesn't have any covers. Okay, it's exceptional. If you take S1, so for any n, there exists exactly one n-fold covering. So okay, so all one manifolds are exceptional. Okay, so all manifolds are exceptional. Okay, now let's look at dimension 2. It's already a little bit more interesting. So let's see whether we can do it together. So perhaps start out with some examples of exceptional manifolds, and then we'll see whether we can do it. Okay, so S2 is exceptional. Okay, I think there's no doubt about that. So let's see. What else? Well, clearly, if you take a surface, if you take a torus, it's exceptional because any finite covering of a torus is again a torus. Then, so sigma G, meaning the closed surface of genus G. So yes, thank you. Orientable. Well, okay, so of course we also know it's exceptional because if you take an n-fold covering of a surface of genus G, well, you know exactly that you know that by Euler characteristic reasons the genus is determined by G and N. So they're also exceptional. I have to admit, like, it's one of the things which to me is like a little bit of a miracle. Like, you take completely different coverings of surface and lots of different coverings. And that they're all the same. And that's a little bit of a miracle. We're just so used to classification of surfaces, but it's not so obvious otherwise. If you just try to do it by hand, I write down a surface, write down two completely different epimorphisms onto groups of size n. Why should they be homeomorphic? But okay, they are. So let's see. Now RP2. Okay. So because it only has one two-fold covering, it says 2. So so perhaps here I should write the R exceptional. Now, okay, so we can just take our favorite random manifolds. For example, I could look at the Klein bottle. So what about the Klein bottle? Klein bottle exceptional or not? Exactly. So the Klein bottle has two-fold coverings, the one which is orientable, but you also have coverings which are not which still stay non-orientable. So in fact, any closed non-orientable surface is not exceptional. Okay, so I think we. Say it? Except for, yes, that's true, yes, thank you. Thank you. Good point, yes. Okay, and now let's also do the case of manifolds with surface with a boundary, just to warm up. So let me give you one example. So here the disk, okay, clearly exceptional. Also, if you take the torus, let's see. Now, if you take the Möbius band, okay, pi1 of Möbius band is that. So again, you only have for any n unique covering. So Möbius band. So let's perhaps now look at the following. So that is a disk minus two disks, or you take a sphere minus 3 open disks. Okay, exceptional or not exceptional? So all, certainly if you take, so the ferment group is a free group. So all index n subgroups will be isomorphic. So subgroups are isomorphic, yes, but does it mean that the covering space are? Second? Yeah, yeah.
Yeah, all the cases we can compute all characteristics.
Yeah.
The number of boundary components.
Ah, yes. Okay, so so it turns out it is not exceptional. So and why is that? So why is that? So perhaps let's do the proof. So if you want to know your surface, you have to know all the characteristic, and you have to know the number of boundary components. And so what we want to do is we want to produce two different coverings which have a different number of boundary components. And how do you count the number of boundary components? Well, you have to look at the image of your original boundary components and see that the size of the image is different. So, for example, what you can do is so let's call them A, B, and C. Okay, so what you can do is consider, I hope I get it right, pi 1 sigma to Z, and then afterwards you go to some Z modulo n for n conveniently chosen. And what you do is, one where you send, okay, now you know that I didn't write down orientations, but let's say A plus B equals C. So you could send like A to 1, B to 0, C to 1. So then the B doesn't lift, so you get lots of boundary components. But you could also take A to 1. Now I've got to be careful. B to 1, C to 2, and now I guess if you take n equals 5 or whatever, then you will see that your coverings have different number of boundary components. Okay, so that was just to warm up, and I guess same argument should basically take care of all surfaces with the boundary, which I didn't already list over there. Okay, and all other surfaces with boundary, so other meanings, ones which I didn't write down over there yet, are not exceptional. Okay, so I'm using a little warm-up exercise. Okay, so now let's move on to 3 manifolds. So dimension equals 3. So what can we say about 3 manifolds? Yeah, so let's write down a list of so let's write down examples of say closed, just to warm up, closed let's say prime 3 manifolds that are exceptional. I should say we didn't completely settle yet on the name exceptional. It's like a working name right now. So the other name under discussion is virtually constant or virtually the same. But if anybody has a great idea for how to call these manifolds, let me know. Anyway, okay, so let's look at examples of closed prime 3 manifolds which are exceptional. So somebody daringly already said S3. Okay, any other offers?
It's not prime. S3 is prime.
S3 is prime by definition. I guess 1 is not a prime number, but S3, well, fair enough, yes, okay. Yeah. Okay, so let's see any other examples. Length spaces, yes, so that's very, very good. So because then, of course, pi1 is cyclic, so, okay. So pi1 cyclic, of course, also reminds us of S1 times S2. And, well, it's also pretty clear the 3 torus is also exceptional. And then the question is whether that's it or not. So let's see. So if you want to answer such a question, so what do we do? Well, okay, so prime 3 manifolds closed. Evidently, one wants to look at the J decomposition and all that. So let's perhaps first do the case where you have a trivial J decomposition. And then there are basically 3 cases to worry about if you have trivial J decomposition. You have a hyperbolic case, which we'll talk about in a second. You have the Seifert-Weibert case, but then if you look at, as we will also see in a second, a Seifert-Weibert case, Seifert-Weibert case, you have to break it up into 2 parts, namely spherical or non-spherical. So, and in fact, the spherical ones took us quite some time to figure out, because you never want to look at spherical manifolds properly. But so we did the exercise, so which took 1 or 2 afternoons. So we looked at spherical 3 manifolds, and so how do you do that? And when you look at your favorite book on 3 manifold groups, and then you see there are basically 4 infinite families of 3 manifold groups. One is length spaces, and then there are dihedral or dihedral times something cyclic, and then something called P something, and something called Q with a parameter. And so we did the finite group theory exercise, and we found, let's see, I always forget the answer. So that Q4, and it doesn't really matter what it is, because also I don't know right now. But these are like an infinite family of spherical and 3 manifolds, and then you can also do times some cyclic group, which is such a K is co-prime to 4n, so they are exceptional. Okay, I mean, one of those things we have to do in a paper to make it complete, where you never want to reach the proof. Unless, of course, you're trying to find a nice exam problem for your group theory course. Okay, so, I mean, and then all of the other spherical guys are not exceptional. All other spherical ones are, sorry, I apologize. So, is it a problem with exceptional? Like, it's exceptional for 3 manifolds now exceptional or is it non-exceptional? So, these are not exceptional, and all the other ones are exceptional. Except, I have to admit, there's one little exercise we didn't do yet. We didn't do the Poincare homology sphere yet. Must be obvious, but we didn't do it yet. And let me just write down. So there's the fundamental group of the Poincare homology sphere, where we didn't do the exercise yet. And then also there's P48, which I have no idea right now what it is. So we didn't do the exercise yet. But so basically we settled all the spherical cases. And it's not particularly entertaining. Okay, so now let's look at closed Seifert-Weibert spaces, and then afterwards we look at closed hyperbolic manifolds, and then afterwards we worry about J decompositions. Okay, so lemma. So if N is a closed Seifert-Weibert space, and then I guess I should say none of the above. Then n is not exceptional. Okay, so let's see how would you prove such a statement. None. Okay, so my favorite fact about Seifert-Hilbert spaces is that they are finally covered by an S1 bundle over surface. So without loss of generality, n is an S1 bundle over a surface. And so clearly, like here, so since it's important, like here my definition, I did not say anything about regular covers. So if you want to show they're non-exceptional, it suffices to find a covering which is non-exceptional. Okay, and now, so you can write as an S1 bundle over your surface. And another nice fact about Seifert-Hilbert spaces is that the Seifert-Hilbert structure is unique except for a couple of annoying special cases which we already excluded. Like for example, like length spaces don't have a unique Seifert-Hilbert structure. The 3 torus doesn't have a unique Seifert-Hilbert structure, but they're already all excluded. So this structure here is unique. And perhaps let me just first do case 1. Case 1 is when it's a trivial bundle, S1 times sigma. And now it's clear that we are done.
You compare with orientable case or?
So perhaps initially I want to do orientable. Let me just say, okay, let me just do orientable throughout. I mean, if you want to show something is non-exceptional, then you can always go to finite covering, and then you somehow, perhaps I'm missing now 1 or 2 items in my list of exceptional manifolds. So let's just do exceptional, orientable, just to make it slightly less confusing. Okay, so now if you have S1 times sigma, well, you're done, because sigma is not S2, because I already excluded it, and then it's clear we're done, because now you can take cyclic coverings corresponding to the S1 term, so you get again S1 times sigma, or you take cyclic coverings corresponding to sigma, so you increase the genus. Okay. So that wasn't so hard. And case 2, well, it's similar. I mean, you have to work just a little bit harder. So, I mean, you can always take finite coverings corresponding to the sigma. And now what you have to do is, well, you also want to play the same trick here. So you want to have a finite covering which somehow sees the S1 factor. Now you can no longer just take a billion covering spaces. But since pi1 of n is residually finite, you can always find the homomorphism from pi1n to some group which is non-trivial on the S1 term, and then you're basically done. Okay, so it takes a little bit more effort, but not much more effort. But it's basically the same, very simple idea. Okay, so evidently the most interesting case, or I guess one which most people care about perhaps, is the hyperbolic case. So let's see how we do the hyperbolic case. Okay, so well, that's called proposition. It's not that hard either if you have the right idea. So hyperbolic manifolds are non-exceptional. Okay, so that's of course not a surprise. The only question is how do you do it? And I guess when you hear, like when you see such a problem, one good question or one amusing question is always, could you have done it before Agile-wise? So can you only do it with Agile-wise? I can only do it with Agile-wise. So if somebody has a pre-Agile-wise solution, we'll be happy to listen to it. Okay, so we need some way to distinguish hyperbolic manifolds. Well, I'm really just like a dirty topologist. I'm not a geometer, but it's good to have a geometer, namely Bram, on the team. So he suggested to look at the following. So we look at the geodesics in hyperbolic manifolds and at the systole. So we need the following facts, which I guess are well known to most of the audience, who are perhaps much more geometric than I am. So first of all, any free homotopy class can be represented by a geodesic, and the geodesic is unique up to reparameterization. So any free homotopy class is represented by a unique up to reparameterization geodesic. And the second thing you need is that, which I was certainly not aware of before Bram told me, just tells you how little I know, that the number of, so if you give me a bound L, the number of geodesics of length less than L is finite. Okay, so, well, perhaps I can put it here. So for all L, the number of geodesics of length less equal than L up to, that's again just a reparameterization, is finite. Okay, so now how does it help us? Some proof of a proposition. Okay, so perhaps okay, define the systole of a hyperbolic manifold. So n hyperbolic is the minimal length of geodesic. Okay, so that's a tool we want to go into the proof. So with the systole, and so the idea is so that given a hyperbolic manifold, we would like to find covering some same degree, but where somehow the systoles differ. So that's the idea, and so how do we do that? So well, we want so we want to build two sequences of covering spaces. One where systoles is bounded, and the other one where the systoles go off to infinity. And so here, I guess, is the one trick we have to use without the loss of generality. B1 of n is greater equal than 1. So remember, so we can always go to finite coverings, and then Ian Agel tells you that given any hyperbolic three-manifold that exists a finite covering, such that the first Bain number is at least 1. So here. Okay. I mean, it's conceivable that perhaps one doesn't quite need the full power of that statement, but it certainly makes our argument significantly easier. And so define, so let's say n tilde k, so that is the covering space of n corresponding to pi1n to z modulo k. So covering corresponding to the homomorphism from pi1n to, onto z. I don't really care which one, I just take an epimorphism onto z and then to zk. And then the cheap observation is that the systols of n tilde k, so they are bounded. So systols of n tilde k, if you look at that sequence, and why is that? Well, that's just because you look at the kernel from pi1n to z, it's non-trivial, and then take any element in it. It's represented by, you can represent by geodesic, and that lifts to all finite coverings. So it's really bounded by, well, systole of the kernel from pi1n to z, if that makes any sense. Okay, so that's a bounded sequence. And conveniently enough, here also any, so here for any degree we can find covering. Okay, and now what we also want to do is we also want to find finite coverings where the systols go off to infinity, and that is easily done. So on the other hand, what? We can find a sequence n. Already used tilde, so let me use hat k of finite coverings. Such that the systole of nk hat goes off to infinity. And so why is that? So you give me any c, whatever large, and now we know that the only finitely many geodesics of a length less equal than c. And so now I just have to ensure that none of them lifts. And how do you do that? Well, we know that pi1n is residually finite. So you just have to, so for each of the finitely many geodesics here, you find a homomorphism to a finite group such that that geodesic gets sent to a non-trivial element. And if you're a little bit nervous, you can make it into an element of arbitrarily high order. And now you just take all these homomorphisms to a finite groups, and then take the direct product, and then just take the image of pi1n into this, in the direct product of these finite groups, and then you find a finite covering such that the systole is larger or equal than your original C. Okay, so here, so here let's just say use, so here we use the 1, and here use 2, and the fact that pi1n is residually finite. Okay, but now we are done, because here, so I already put my box here, just say it in words. So here it's bounded, let's say by some C, and now here we know there exists some finite covering such a systole is bigger than C. Now look at the corresponding degree here, but here all degrees appear. So it's one thing which is really useful about this fact here, that you get a sequence where all degrees appear. I mean, without acknowledging that, you can surely also, you can also construct a sequence with systems stay bounded. Is it true? That's not entirely obvious. Not entirely obvious, yeah. Yeah, okay, yeah. So, the proofs in threefold topology where AGL is absolutely essential, and perhaps here with a little bit of more work you could do without Ian, but we all like to cite Ian, and it's so convenient, so let me use Ian here. Okay. Okay. Now, what else? Okay, now we have to look at non-trivial J decomposition. So, what happens if you have non-trivial J decomposition? So, proposition, if n has non-trivial J decomposition, then n is not exceptional.
So what about Solomon?
Good question, yes. Proof case 1, Sol manifolds. Yeah, you're absolutely right. So Sol manifolds will certainly be different. So how do you do Sol manifolds? So what are Sol manifolds? Well, at least up to going to finite covering, they are a torus bundle over S1. So I can assume, so without loss of generality. So it's a torus bundle over S1, where the monodromy has 2 real eigenvalues. And now what you need to do is, okay, now again you want to find the different covering spaces. So there's, okay, so you look at ones where you unravel the S1, and so what happens to your eigenvalues of your monodromy? Well, you take powers of your eigenvalues in your, so here you have lambda 1, lambda 2 are the eigenvalues of the monodromy. Now if you take if you go here from S1 to, from pi 1 S1 to Zn, then what you do is you take powers of your monodromy, so your eigenvalues, you take powers of your eigenvalues. On the other hand, and then what you can also do is, look at, so you have pi 1 of T2, and now you take a characteristic subgroup. So you have Z2, and now you take a characteristic subgroup like KZ plus KZ. And then that defines you a subgroup of pi 1n of order k square. But that is diffeomorphic to your original Sol manifold. So it requires a little bit of thought. And so it's again, there's a trick, a little bit like before. You want to take different coverings, one coming from here, and one, perhaps a little more effort, coming from here. But I think it's okay. But yeah, also makes me a little bit nervous. And the same should also work for Neal manifolds. Okay, but actually it is so Neal manifolds is actually important because it really it's good that you mentioned it because our proof it really has to distinguish torus bundles and non-torus bundles. Okay, so case 2. Well, everything else, and again we want to play the game of finding finite covers which we can distinguish, and I guess by now it's clear, also like from the arguments we had before, you always want to take some, you don't want to take really take an algebraic invariant, you want to take something geometric topological. And so what we want to do, use this time is we want to use a little bit like before with the surfaces, where we looked at number of boundary components. So now we want to look at number of J tori. So that's the idea. And now, so we want to find different coverings with different number of J tori, but same degree. And well, it's like a more fancy version of the argument from up there. So if you want to get a different number of J tori, well, okay, first of all, if you have a three-manifold, if you take a finite covering, then the J tori of the finite covering of the pullbacks of the J tori downstairs, except for a couple of slightly annoying counterexamples, for example, like Sol manifolds. So there the number of J tori is always 1. And there's a slightly annoying issue if one of your J components is a twisted I bundle over the Klein bottle. But okay, so the first thing we do is we go to find a covering where we don't have a J component, which is a twisted I bundle over the Klein bottle. So once you're there and you're not a Sol manifold, not a Neal manifold, then your J decomposition behaves exactly the way you want it to behave. Okay, we'll not write down, but there's little things you have to do at some point. Okay, and now as before, so we want to play the game of finding homomorphisms to perhaps even cyclic groups, such that the images of the J tori are different. And now here for surface it was sort of easy. For J tori you have to work a little bit harder. And so I guess the key technical step is the following. So key step. So there exists a finite cover n hat, let's say, and a J component n hat, well, let's call it m hat, such that or perhaps just say that without okay, just such that so if you look at the co-kernel of the H1 of the J tori in H1 n hat, so that the rank thereof is greater than 1. So that's so you want them to get to a point where the J tori do not cover all of homology, or even rationally. And so that's, I guess, the technically least amusing proof of the paper to read. So how do you do that? Well, you start out with a J component, and now since we excluded Sol and Neal manifolds, we know that no J component can be a torus times an interval. And so if you have a three-manifold with a toroidal boundary, you can always find a finite covering such that the interior of the homology is non-trivial, meaning given any three-manifold which is not T2 times an interval, and perhaps one of the other stupid examples, you can always find a finite covering such that the co-kernel of H1 of the boundary tori into H1 of all of it has non-zero rank. Okay, that's a little bit of messing around, but okay, that can be done. And now, so you first do it for one J component where such that the bounded tori, which are just the JJ tori here, have a non-zero rank, and now you have to extend this finite covering of your JJ component to all of the three manifold, and then you have to work a little bit harder. I mean, like that's just in some sense like that's sort of semi-classical 1980s and 90s three-manifold topology you have to do. I mean, by the time you've written it down, it's 2 or 3 pages, but it's good old messy group theory. Okay, and so once you have yourself convinced of that, well, then you are almost done, because now what you want to do is so now again, without loss of fraternity, we're already at that point here, and now you do 2 things. Namely, one is consider so you want to pick a map to Z from H1 n tilde, which vanishes on all JJ tori. So consider or pick H1 n tilde to Z such that let's call it phi restricted to each JJ torus is 0. So that you can now do. And so if you take such coverings, then the number of JJ tori multiplies, and you can realize any degree. And now the only thing you have to do is you have to find a covering of any degree with the number of JJ tori doesn't multiply. So all you have to do is you have to find you just take any covering which is non-trivial on any of the JJ components, on any of the JJ tori, and that you can do because pi1 is residually infinite. Okay, so pick any pi1n to a G finite which is non-trivial. On a JSJ torus. Okay, so that takes care of the case of closed prime 3 manifolds. And let's see, what else do I want to say, if anything? So, okay, so if your boundary boundary is toroidal, well, you basically play the same trick as over there. So if you have toroidal boundary, okay, if you exclude your stupid cases like S1 times D2 or something like that, then again you find finite coverings with the number of boundary tori is different. So just very similar to that argument. And now you can also do non-prime manifolds. Well, okay. Then, can anybody think of a non-prime manifold which is exceptional? So I think we could think of one infinite list of examples. Then we take a connected sums of S1 times S2. And I think that's it. So basically get a complete list of all exceptional three-manifolds. And perhaps let me just conclude with 2 questions. One, one is, I mean, you can now again look at some type of growth function. Like you look at all n-fold coverings of hyperbolic manifold. Now you look at all n-fold coverings up to homeomorphism. So how does number change with n? You have to be a little bit careful in your formulations. Like you cannot say the number will grow exponentially because if n is a prime, then you only have cyclic coverings, so clearly not much is going to happen. But somehow you would expect that a hyperbolic manifold should somehow have lots of non-diffeomorphic coverings of a degree which is not chosen in a totally stupid way. Okay, so you can sort of try. I mean, it's not. Okay, so we have to perhaps think a little bit about what is the appropriate statement. But can you say that? I know. Look at all coverings of degree n factorial. Then the number of non-homeomorphic covers grow whatever in n. I don't know. And perhaps more interesting is, I mean, all that sort of feels perhaps slightly semi-stupid. Now, what we couldn't do is, so we couldn't find normal covering spaces. So it's like in basically every single argument which I ever gave you, it was always we first go to a setup where everything's nice, and then we continue from there. But we couldn't, I think for none of these cases, we could come up with an argument which works with regular covers. Okay, I think that's kind of an amusing problem to think about. So can you, if you have a normally exception, whatever, can you find a different argument which works? Okay, I think nobody ever complained about an early break, so we'll stop here. Thank you.
Comments or questions? RP3 connected some RP3 is not exception.
Good question. When I was asking my question, was all thinking, let's see, RP3, connect some RP3. But I think...
Could you repeat the question?
I ask if RP3 connected some RP3 could be maybe, I don't know, I have to check, exception or not.
I think it's not. So I guess would you have to...
The group is Z2 times Z2.
No, but I guess what I would try to do is, so I would look at, so you have, so the abelianization is Z2 plus Z2. Now the two obvious things you can try to do. One is you project onto one of the two as Z2s, and the other one is the diagonal projection.
Yeah.
And I would guess they give you different answers.
So one double covering is RP3.
So in one you get, in one
RP3.
you only get S1 times S2. I guess one is S1 times S2, and the other one is you keep one of the RP3 factors. Because like if you take one,
you get RP3, and the other.
No,
Because
so
the double
you look at the
RP3
file
is
cover.
S3.
Yeah, but you take, but on one factor, so you want to do two different twofold coverings. One is where you both unravel the two RP3s, so that in your prime decomposition you don't have any RP3s, which means you only have S1 times S2s. And the other one, you don't want to unravel one of the RP3s, so when you find a covering, you still have an RP3 left. So
I would think.
yeah, okay, I was just think about that.
It also fits into one of the other ones, because it admits a geometry. RP3 connects some, RP3 admits like a Thurston geometry. So it
Yeah, but
already
I'm not sure
fits
what
into
that's-
one of the other cases you've done.
Yeah, but you never know whether perhaps it's one of the cases I wanted to exclude. Because like in some of the geometry doesn't help me. Like what I would use this cipher fiber structures, and it's virtually like an S1 bundle over surface. And so, yeah, okay, like that's perhaps, I mean, people who do a theory for topology know, like you spend like most of your time trying to worry about S1 times S2 and RP3 connects some RP3 and the twisted I bundle of the Klein bottle.
No non-orientable
Say again?
No non-orientable
Well, S1 times R. No, sorry, let's see. Yeah, it might be true, yeah. Yeah. S1 of yeah, it might be true, yeah. I have to admit that's, okay, we're still typing, and I guess we didn't do the non-orientable case yet. But yeah, it sounds reasonable, yeah. It's almost certainly true because...
S1, please, there is two. I know, there are two different, orientable and non-orientable. Thank you.
You off, yeah?
Other questions?
Why doesn't the argument for Why doesn't the argument for the Seifert-Friedl case cover the nil geometry? Nil is Seifert-Friedl's case.
Oh yeah, sin is Seifert-Friedl, yeah, fair enough, yeah. So I just, but it has, okay, but here it has non-trivial shading composition.
Right.
So I didn't want to, okay, like case 2 was, so here my proposition non-trivial shading composition, case 2 was non-trivial shading composition such as no shade component is torus times an interval.
Okay.
But yeah. So yeah, so if you wanted, there are now 2 proofs for nil
Two
manifolds.
proofs for nil, okay.
Other questions?
What if you require that your subgroups are of a certain type and not just have a fixed index?
Well, as I was saying, like if you interpret the normal certain type as normal, it's already very interesting. So like. Yeah, but there are lots of good questions you can ask. Like, I mean, like it's okay. It's like a playing board. Now you just change the definitions and go ahead and start wondering. But yeah, that's one thing we thought about. We didn't think about any variations yet.
So other than surface groups, is there an example of hyperbolic non-exceptional group? So other than surface groups and free groups, is there a hyperbolic group which is non-exceptional?
Why don't you just ask somebody who knows something about hyperbolic high-dimensional manifolds? And I don't, so perhaps Bram would know, but I know nothing about hyperbolic manifolds of dimension 4 and higher. But that's a nice question, yeah.
I just said word hyperbolic.
Oh, but then you don't even know whether every hyperbolic group has a finite quotient.
Okay, so I guess we have many questions and many interesting things, so thank you.
Okay, thank you. Thank you.